start with, we've got this light sinker, and we talked about this in the theory as well, that's being spun around in a circle. The force is this tension over here, and the other force, which I can't really draw very easily, but it's in 3 dimensions, is the weight going down on the sinker. The movement is at a tangent to the circle, so that is the displacement direction. As you can see, the displacement direction is at 90 degrees to the tension, one of the forces, and it is at 90 degrees to the weight, the other force, and therefore you land up with no work being done on the sinker because the direction of movement and the direction of forces is exactly opposite from each other at 90 degrees. You've got a frictionless dynamics trolley. Its mass is 3 kilograms. It's accelerated along a horizontal frictionless surface by a force of 50 newtons, but the force acts at 53 degrees to the horizontal. So that's 50 newtons at 53 degrees, but the movement, the displacement, is going to be in the horizontal direction. So the first thing that I need to do is I need to work out the component of the force that is in the horizontal direction, which means that I'm going to need to use cos, and because it's the adjacent side, and cos of 53 degrees is equal to the adjacent over the hypotenuse. So you land up with the horizontal being 30 newtons, and the force continues to act while the trolley moves 12 meters across the surface. What is the work done? The work done is the force times by the work done is equal to force times distance, which is going to be equal to 30 in the same direction as the 12 meters, and you land up with 360 joules. What is the acceleration of the trolley? Your F is equal to ma. You've got a mass of 3. Your force is going to be in the direction of acceleration, is going to be 30, and therefore you land up with an acceleration of 10 meters per second squared. Now we've got a loaded hospital trolley. It has a weight of 800 newtons, and it is wheeled at a constant speed from one floor of the building to the other floor along a ramp. The length of this ramp is 10 meters. If the ramp is angled at 30 degrees to the horizontal, calculate the work done on the trolley and assume that the trolley wheels are frictionless. So we're going to take a look at that. We're moving the force is in the vertical direction, and therefore we want to move up by however much we're moving up over here. The length of the ramp is irrelevant. We're going through work done, and force and distance need to be in the same direction. So I'm going to say that's my opposite side. So I'm going to say sine of 30 degrees is equal to the opposite, which is my vertical, over the hypotenuse. And I land up going 5 meters up, working against 800 newtons. So work done is force times distance, and that is going to be 800 newtons times by 5 meters, and I land up with 4,000 joules. Another way of doing that would have been mgh. You haven't been given the mass, but you have been given mg, and this is your h. What energy transfers take place in the following examples? A stone is shot from a catapult. A catapult has got an elastic, so it's elastic energy into kinetic energy, or you could even say into gravitational potential energy, because it gets shot up into the air. A bicycle dynamo lights up a lamp. These are all, there are a lot of energy transfers, so there's nothing necessarily specific on them. A bicycle dynamo lights up a lamp. It's by pedaling the bicycle that you light up the lamp, so kinetic energy is changed into electrical energy. Water from a dam. The way that any dam project works is that the dam is high, and then it falls down, and then it flows along in the river over there. So we've got big dam, and then we've got falling. So it's gravitational potential energy, and then that drives the turbine, and then you get electrical energy from that. And then coal, chemical energy, is burnt in order to operate a steam engine that pulls a train up an inclined slope. So there are quite a lot of things that happen here. Coal, chemical energy, then makes steam, which is going to be kinetic energy, which drives the engines, which is kinetic energy, up an inclined slope, and suddenly you've got some gravitational potential energy as well. Those are all happening in that particular. Object of 3 kilograms falls from rest and attains a terminal velocity of 5 meters per second before striking the ground. Calculate the maximum kinetic energy. EK is equal to a half mv squared, which is a half of 3 times by 50 squared, and you land up with 3,750 joules. We've got Table Mountain. The lower cable station is 370 meters above sea level. The upper one is 1,070. So the difference between those two is 700 meters. If the mass of the cable car is 800 kilograms, what is the gravitational potential energy when at the upper cable station relative to the lower cable station? So this is the distance that we're going to go through, and we're going to go 800 times by 9,8, or 10 if you prefer, times by 700. And you land up with that over there. Relative to sea level, now we don't care about the lower cable station. We want to go all the way to sea level. So instead of multiplying by 700 meters, I multiply by 1070 meters, and I get that answer over there. Finally, relative to the highest point on Table Mountain, which is called Maclear's Beacon, and that's at 1080, which means I somehow need to put energy into that system, and I need to get to with 10 meters. So I'm going to go 800 times 9,8 and times the difference of 10, but I need to put that energy in. It's not going to fall. The gravitational potential energy normally means that you can easily fall. This means I actually have to climb with that much energy in order to get to Maclear's Beacon. We've got a ball of mass 0,25 kilograms, and it's dropped from a height of 2 meters, and it bounces. What is the potential energy of the ball just before it's released and at its highest point of rebounding? So the first thing is we're going to go potential energy is equal to mgh, and it's 0,25 times by 9,8, and in the first case it's 2, and in the second case it's 1,5 as your height, and you get those two answers. And why doesn't the ball bounce to its original height? Because some of the energy is lost to heat and sound during the bounce.